That's right. Time to teach. It is 11:10 a.m. on a Sunday, and so that means it's time for some sort of econometrics. This is not a lesson for either class explicitly. This is just an example that I remember from my graduate school econometrics classes that stuck with me, and I think speaks a little bit to the sort of math and models that epidemiologists and public health officials are sort of using these days in this crazy kind of public health crisis that we're having with regards to the coronavirus. So I don't really know what the point of this video is other than that I just really like this example, and to me it's a little comforting to know the sort of math that is going on and the sort of tools that are in place to think about measuring infectious diseases and stuff like that. And so I'm going to go ahead and show you this kind of quick example. Let me set things up so we can go to the whiteboard. All right, so the method of moments, this is it's a statistical technique much more than an economic or econometric specific one, and it's a way of finding multiple parameters or finding parameters through single pieces of data or single sets of observations, and I think that'll make a little more sense in a second. So the first example that I'll give is if we consider a coin, and a coin, you flip it, and either 1 is a head or 0 is a tail. Ultimately, a coin, so say you don't know the probability of the coin, whether it comes up heads and tails 50-50, whether it's 60-40, 70-80, 80-20, and so you want to estimate p hat. That's sort of the parameter that you're interested in for this coin. You want to find out the probability that it comes up heads. And this is almost a trivial example, but what method of moments says is, well, if you have a coin, we know that the expected value of the coin is p. That is to say, if you have a coin that comes up heads 60% of the time, on average, when you flip that coin, you're going to get a 1.6 or 60% of the time. So a pretty good estimation for the parameter p is just to use, in this case, what's going to be the average of your flip. So maybe C bar for coin bar. So if this were our data, if we had no other data than this, this is saying the best guess you could make as to the probability of this coin is 60%, which is almost trivial, but certainly as the sample size grows, if you flipped a coin 500 times and 60% of the time it's come up heads and 40% tail, 60% is going to be a much better guess for the likelihood of the coin than is a 50-50 coin or a 70-30 coin or something like that. So we're going to move, though, from the coin example to what is called the binomial distribution. And so the binomial distribution describes a situation where sort of each day or each observation or each trial, you have n things happening, and they get observed with probability p. So I'm going to call n the number of occurrences. I'm going to call p the probability that the occurrence gets reported, or probability of reporting. And then that leaves x, the number that we're going to observe, as the observed number of reports, or the observed successes, or the observed things. I'll call it observed reports. So when I first learned about this sort of method of moments for the binomial distribution, the example that I was given is that n is the number of crimes occurring in a city each day, perhaps, and p is the probability of that crime getting reported. So lots of crimes get committed, but maybe go unreported because either the person who is the victim of the crime either doesn't notice or chooses not to report, thinks it's not important enough, doesn't feel comfortable reporting. And so the fundamental problem and the kind of the question that this method of moments helps us deal with is that what in my example, a police department would observe is going to be X, which is they observe the number of crimes that show up, that get called in each day, but they know that that's not the true number of crimes that there are in the world. In relation to kind of the pandemic that we're dealing with in the US right now, X could be the number of known cases of the virus that you see in a given day, but we know that that number is not the true number of cases because there's some true number of either crimes being committed or coronavirus cases, and then there's some probability p that each of those cases gets reported. And so what we observe is neither the true number and it doesn't tell us the probability being reported. But so what method of moments does is it's going to let us take this single number and then back out what n and p are most likely to be. So we take a single kind of vector of data, a single column of data, and then we're able to get two parameters from it. And so how do we do that? Well, if something follows the binomial distribution, just like with a coin where the expected value of a coin was equal to p, the probability that it lands heads, the expected number of reports on a given day, I'm going to need all the space I can get, so I will. The expected value of x is going to be equal to np. That is to say, on the average day, how many crimes get reported? Well, it's going to be the number of crimes multiplied by the probability that get reported. That doesn't mean that every day you get the exact same number of reports. It's sort of like if 100 crimes get committed each day, and each crime has a 20% chance of being reported, each crime reaches their hand into a bag with 4 red balls and 1 blue ball and pulls it out, and if they happen to pull the blue ball, they report. So on any given day, you might have 24 crimes reported, or 18, or 20, or 22, or 37 would be less likely than the others, but still in the range of possibilities. Okay, so we have this column of data, and we still have 2 parameters. We still have kind of one equation with 2 unknowns, and so that's not going to be enough for us to solve for n and p. But we also know, if you do sort of the math on the binomial distribution, we know what its variance is. And its variance is equal to np times 1 minus p. This formula is in any old textbook if you look up the binomial distribution, and so n and p times 1 minus p, this sort of indicates that as p, which is a probability, so it's between 0 and 1, when it's close to 0.5, 0.5 times 0.5 is in decimal world, a relatively big number. That's higher variance, whereas if p was close to like 100%, then you'd have something like 0.9 or 0.99 times 0.1 or 0.01, that number is going to be much smaller. So in other words, as the certainty of reporting goes towards 100 or goes towards 0, the variance of this model goes down. Okay. All the method of moments says, the sort of statistical method, is that the sample moments, which is to say the sample expected value and the sample variance, are pretty good approximations for the true expected value and the true variance. That's it. That's the whole method of moments. A moment refers to an expected value or a variance, and so the method of moments just says, let's use our sample to estimate the true parameters. Same thing we do all the time in econometrics, just a slightly different version of it. So we have 2 columns of data here. I'm imagining that these are sort of 2 different cities or 2 different scenarios, and these are maybe the number of crimes that get reported. City A has, over the last 5 days, 8, 9, 10, 11, and 12 crimes reported. City B has 7, 8, 9, 11, and 15 crimes reported. For both of these cities, the average number of crimes is 10. The sample variance for each of these cities, and this is digging back into your statistics memory bank, but the sample variance, the variance of a sample, is going to be 1 over n times the sum from 1 to n of xi minus x bar squared. And the sample variance of xa, in this case, I believe is 2. Let me double check my notes. Yep. And the sample variance of xb is 8. So if you ran these 5 numbers through this formula, you'd come up with 8. If you ran those 5 numbers through this formula, you'd come up with 2. What the method moments is going to do is it's going to say, let's assume that n hat, our estimate of the total number of crimes committed, and our estimate of the probability that a crime gets committed, is equal to x bar. That is to say, the average of our sample should approximate the true population average, and our estimate of the variance should approximate the true variance. So we're also going to say that n hat p hat times 1 minus p hat equals our sample variance. And now it's just going to be a matter of plug and chug. So if, I'll give myself a little more space where, oh no, I can write a little lower. Sorry, I'm trying to look at my video and see how low I can go here. About there is where my video gets cut off. Okay, so we can now plug, if x bar is equal to n hat times p hat, the sample mean is our best guess for the population mean. We can plug x bar in for here, and I'm going to rearrange this equation a little bit so you get that x bar times 1 minus p hat equals s of x. Divide both sides by x bar to get that 1 minus p hat equals s of x over x bar. And then I'm going to add p hat over to this side and subtract that back, and you get that 1 minus s of x over x bar equals p hat. And so with that, for xa and xb, we can now say that, so s of x for our first sample is 2 divided by 10, so our p hat a is going to be 0.2, and our p hat b is going to be 0.8. And now we need to find n hat for both samples, and so if x bar equals n hat times p hat, and x bar is going to be 10 in both of these cases, for sample A, n hat is going to be 10 divided by 0.2. So n hat A is going to be 20. No, sorry, 50. 10 divided by 0.2, yeah, it's going to be 50. And in our second sample, n hat B, we are going to have 12.5. Did I do that right? I did not. 9, 10. Oh, so, okay. Here's where I screwed all this up. I forgot to do the 1 minus. So, sorry guys, this is live. I'm not going to go back and re-record all of this. In our first sample, the sample variance is 2. So 2 divided by 10 is 0.2. 1 minus 0.2 is 0.8. So our p hat A is 0.8. And accordingly, our p hat B is going to be 0.2. And so now, all right, now this is right. for sample A, the mean is 10, the probability had is 0.8, 10 divided by 0.8 is 12.5, and for sample B, 10 divided by 0.2 is 50. So for sample A, our estimate is 12.5, 0.8, and for sample B, our estimate is 50, 0.2. And so here's the striking difference between these two samples. These two sets of data look, in my mind, fairly similar to each other. Sample B is obviously a little more varied, but not that much more. They both have the same mean. 15 is a little higher than 12, but not a huge difference. But what would the method of moments tell us? The method of moments says that these 5 numbers most likely came from a population where, on average, 12.5, let's say, crimes are committed each day, and they're reported with 80% probability, whereas these 5 numbers most likely came from a city where 50 crimes are committed each day, and crimes only get reported with 20% probability. So these are the sorts of calculations that epidemiologists are doing. They're going to different cities' numbers of cases and trying to ask themselves, all we have is the observed number of cases, which is a combination of the true number of cases and the probability that a case gets reported. How can we use that data to try to back out the overall likely number of cases that are happening either across cities or across countries? And method of moments is going to be the baseline for how a lot of these calculations happen. Obviously, in this case, you have to take into account a lot of extra factors. The fact that your data might not be independent, the number of cases from one day to the next has codependencies, and that the n, the number of cases day to day, might be changing. It's not kind of a fixed number. You'd have to estimate this model with a sort of growth factor in it, but still, the underlying math is there, and so now you know a little bit more about epidemiological research than you did before. All right, take care, guys.